All right, let's take care of part B. We have arc10x squared to be integrated. Well, you can use the known techniques of integration again to find the value of this definite integral, but you may rely on to integration by parts. You can try that out, but this is a complicated integral, so that's why we're using the power of the power series to approximate these integrals with the error less than 10 to the minus 4. So arc10x squared resembles arc10x. You can in fact reproduce arc10x squared out of arc10x by looking at its power series. So let's go back to the power series for elementary functions table to grab the power series of arc10x. Arc10x has this like nice representation, and the interval of convergence is, as you see, like -1 and 1. Okay, so I'm going to grab this and then put it back into the formulation. So let's see what we have now. Well, I have arc10x listed down here with the power series representation. This is the an term. And I have arc10x squared. All I do is just replacing x by x squared in the power series of arc10x. Okay, so that's good. So we have -1 to the n, x to the 4n plus 2 divided by 2n plus 1. So now I can do the integration here. Okay, I can do the integration here. Integral from 0 to 1/2 arc tan x squared dx is the integral of, in fact, the infinite series. Okay? And all I'm going to do is like term by term integration. So the infinite series -1 to the n x to the 4n plus 3 divided by 4n plus 3 and 2n plus 1, and this should be evaluated at the lower and upper limits. Okay, so here I'm going to plug in the upper limit. Okay, so upper limit is 1/2, so let's just do that. So you have -1 to the n 1/2 to the power of 4n plus 3, okay, all divided by 4n plus 3 and 2n plus 1. And what happens if you plug in 0 for x? Well, if you look at the expansion here, the power series expansion, all of the terms come with x, right? So when you plug in 0 for x, and that is not going to contribute anything because everything is going to be 0 from the lower limit. So now I have this nice alternating series, and I want to approximate that at this moment. Please pause the video and then revisit the alternating series remainder theorem, which tells you how you can find the upper bound for the alternating series by looking at the n plus first term, because the absolute value of the error cannot be greater than an plus 1. Okay, and who is an in that regard? Well, an is this whole chunk here, right? 1/2 to the 4n plus 3 divided by that is your an. So I would go ahead and you can pause the video anytime, and then you can do this by yourself. A1, I list A1, A2, A3, A4, till, and evaluate obviously those, and until you get something 10 to the minus 4, okay? Less than, once you get something less than 10 to the minus 4, it's the time where you stop listing the elements, okay? So please do this right now and use your calculator, and I'll list all the values here. In fact, I'll tell you where to stop. All right, so I tried to list a few terms of an for you to see what's going on. And you can go ahead and calculate each of those values by using your calculator. But one observation here is that the approximate value of A1 is at the level of 10 to the minus 4, but it's 2 times the 10 to the minus 4. So that's not something we're after, because that's still too big, okay? So we want the error less than to be like 10 to the minus 4, so you have to go to A2. And A2, I can tell you what it is. This is approximately equal to 0.0000 let me see, let's just round that number 5. Okay, so it's at the level of 10 to the minus 6. That's awesome because we're going to stop right here. Okay, that means that if I keep only 2 terms, a0 and a1 in the sum, the error would never ever be greater than 10 to the minus 4, because here a2 is something less than 10 to the minus 4 already. So the summation of the first 2 would add up to what we want at the end. So it's a0. It's all about a0 minus a1, because we have an alternating series and then involving only 2 terms. A0 minus a1 is going to be approximately equal to, let me just grab that for you. So that's going to be approximately equal to 0.041. If I round that number, it's going to be 3 here. Okay. So double verify, and then also find the approximate value of that to plug in here. Okay, so don't round anything off at the beginning. Once you're done of subtracting a0 from a1, then round the number and get the approximate value of the integral. So as you see that the power theories are very powerful to estimate the values of integrals, make any kind of like estimation, because in this case like everything boiled down to an alternating series and approximation of that took us back to the alternating series remainder theorem. So this was a good application of the alternating series remainder theorem to make the approximation, coming with the error less than 10 to the minus 4, and the minimal number of terms you retain in the sum is just 2, a0 and a1. All right. I think that takes care of part B completely, and that makes the end of the video. Thanks for watching, and always, if you have any question or comments or suggestions about these videos, please send those feedback to my way. All right, bye.